Hi, this is Abe. Welcome to the final part of my walkthrough of the 2009 Methods Exam Paper 1. We're up to question 9 now, only this one and one more to go, so let's go down to it. Question 9 says, solve this equation. 2 log ex minus log to the base e of x plus 3 equals log to the base e half. Solve this equation. How do you start? The first thought is get rid of logs. They're hard to deal with, right? Get rid of logs. You can do this using some log laws, right? So you should know that this first term, 2 log ex, can become log to the base e of x squared, right? And then you can use your other log laws to combine logs and hopefully make life easier for yourself. So if you combine this, you know you get x squared on top, x plus 3 on the bottom, log to the base e half. Yeah? So look, the insides are the same and you can sort of cancel the logs out pretty much, right? Key things to look out for, and they could be very mean to trick you on this, but there are some values that x cannot equal. First of all, x cannot equal minus 3, right? Otherwise the inside doesn't exist. Also, log of 0 is not defined. X also cannot equal 0. Keep these two facts in mind. Hopefully you won't need them, but maybe you will. Okay, so on to the nice part. So you know you can get rid of the logs and you get x squared over x plus 3 equals half, right? And if you were to expand this out, not expand, but multiply this out, you'll get 2x squared equals x plus 3, and you get a nice quadratic to solve. 0 equals 2x squared minus x minus 3. In an exam situation, I'm not sure whether you want to do that 2 brackets match thing. It is often easier, requires less thought just to use the quadratic formula. So I'm just going to do that, okay? So x equals negative b is 1, plus or minus root of b squared, 1, minus 4 times a is 2, times c, minus 3, all over 2a. Okay? So that's going to be 1 plus or minus 1 minus 4 times 2 times minus 3. 1 plus 24 is, oh look, plus or minus root 25. So it's going to come out okay. So 1 plus or minus 5 over 4. So i.e., or 1 minus 5 over 4 is going to be negative 1. 1 plus 5 over 4 is going to be 6 on 4, or 3 on 2. There's your 2x values. Now you expect 2 because obviously you're solving quadratic. Looking back up here, minus 3 and 0 didn't appear. No nastiness from the examiners. Thank them for that. And move on to the next question, which is the final question of this exam. So our last question. It says use the relationship f of x plus h is roughly equal to f of x plus h times f dashed of x for a small positive value of h to find an approximate value for the cube root of 8.06. Okay, I hope you've seen this formula before, and I hope you know that it relates to linear approximation, because if you don't, you're stuffed. But anyway, knowing this relationship, you say, okay, there's a function I'm trying to approximate here. Now what do you reckon that function could be? Look at, you want the approximate value for the cube root of 8.06, right? So the first thing to think is the function you're interested in is the cube root of x. Further clue is that you know that the cube root of 8 is equal to 2, and the cube root of 8.06 is going to be pretty close to that, right? So all signs seem to point towards this fact. So let's write down what we know already. Now, f of x plus h, well, you also know that h is obviously going to equal 0.06, right? So f of x plus h, I'm going to write down the formula again for you, so you can see clearly what I'm doing. Okay, so remember f we said was the cube root, x plus h. X is going to be 8, h is going to be 0.06. So there's our value that we're trying to find. That's going to be approximately f of x. F of x is the cube root of 8 plus h, 0.06, f dashed of 8. There, look, we've set up our equation. All we need to go ahead and do is find f dashed of 8. Not hard, right? No, not really. So, first of all, perhaps f dashed of x is, now you know how to do that, right? If f of x equals cube root of x, so cube root of x is x to the power of 1/3. So f dash is 1/3 x to the power of negative 2/3. And so f dashed 8 is just going to be, well, 1/3 times 8 to the power of negative 2/3. To make your life easier, do this. 1/3 times 1 on 8 to the power of 2/3. Right? Easier to comprehend. 8 to the power of 2/3. Always do the bottom part if possible. So 8 cube root of 8 and then square that. Cube root of 8 is 2. Square that, you get 4. So 1/3 times 1/4 gives you 1 on 12. So therefore, cube root of 8.06 is roughly equal to, right, what we said before. So just using this line here, like that. Cube root of 8 is 2 plus 0.06 times 1 on 12. 0.06 is, what is it? 6 on 100. Right, so it's easy if you just put things in fractional form. 6 on 100 by 1 on 12. And you'll get 6's cancelling out, you get 1 on 200. 2 and 1 on 200, which is 2.005. There, that's your final answer. There you go. Cube root of 8.06 is roughly 2.005. Now comes part B. The final part of the last question says explain why this approximate value is greater than the exact value for the cube root of 8.06. This is a hard question. In fact, only 8% of people who actually took this exam actually got marks for this thing. So, for this to happen, you actually need to know a little bit about how linear approximation works. So, I'm going to draw you a quick diagram. Quick diagram of what's going on. It also helps if you know the shape of the graph of a cube root. So, it's going to look a lot like a square root kind of graph, actually, except it sort of goes away. It kind of goes like this, and it gets very flat very, very quickly. Kind of does that, right? So let's pretend that 8 is here and 8.06 is there, right? And I'm just going to show you what exactly the approximation looks like. So in linear approximation, what you do is at your point x, which we defined as 8 before, you draw a tangent, right? So that's a tangent at the point x. or 8. Now essentially, in linear approximation you say, well, the gradient isn't going to change very much, so I'm just going to assume the gradient at 8.06 is going to be the same as the gradient at 8. Now you know that's not true for any curve that's not straight, but you know that this is approximate, and it'll be largely good enough. But look what happens. Our graph, the gradient gets flatter and flatter, doesn't it? Gets flatter and flatter and flatter. So our linear approximation thing doesn't take that into account. So basically, this thing here, use a different color, that's our estimate. Our estimate is here, but the actual value is here. Do you see that the approximate value is greater because the gradient of the cube root of x is decreasing from 8 to 8.06? But if it were increasing, we'd actually be underestimating it, not overestimating. So how would you actually write this? It helps if you draw that diagram, because it shows your understanding of linear approximation. But perhaps you could say something along these lines. You could say the gradient of the cube root of x decreases as x goes from 8 to 8.06. Well, in fact, it decreases as x increases from 0, right? So our straight line estimate will be too high, as it assumes unchanging gradient. There. So just an explanation of what I said before. But essentially it's just because the gradient of the cube root of x decreases, and so the function doesn't increase as much as our estimate thinks, because the estimate thinks that the function is increasing at a uniform rate. Hence we use a straight line. But we know that's not the case in all lines that are not straight. So there you go. The Methods 2009 paper 1 out of the way in well under 1 hour. I hope this has been really helpful to you, and I hope you've enjoyed yourself. I'll see you next time.